Welcome back to The Explainer. So, as folks who already follow data and research, you know that statistics is way more than just, complex math formulas scribbled on a chalkboard. Today, we're going to totally strip away the equations and look at the actual philosophy of the field. And what we're going to discover is that at its core, statistics isn't really about math at all. It's about something way more fascinating and honestly a lot more applicable to how we understand the world around us.
Okay, let's dive into this incredibly refreshing perspective from our source material. Our guide through all this, Mike St. Antoine, offers this brilliant definition. Statistics is basically a way of putting a number on coincidences using probability theory. Just let that sink in for a second. We aren't trying to prove absolute universal truths with impossible formulas. No, we're simply taking everyday coincidences, the kind you notice literally all the time, and using a logical framework to assign a specific, measurable number to them. It's essentially a tool for measuring exactly how surprising a particular event really is.
Section 1. Mathematics of a coincidence. Let's kick this off with a little thought experiment.
Imagine I hand you a coin. Now, it might be perfectly fair with a standard 50-50 chance of landing on heads or tails, right? Or it might be a heavily biased weighted trick coin designed by a cheater to almost always land on heads. So here is the impossible question I really want you to ponder. How many flips of this coin would it take for you to know with absolute 100% certainty that the coin is biased? What would satisfy your skepticism? Would you need to see it land on heads 3 times in a row? 10 times in a row? What if you sat there and watched it land on heads 1,000,000 times in a row? Where exactly is the line of absolute certainty?
Well, let's compare a couple of scenarios. If you flip the coin and get 3 heads in a row, you'd probably just shrug. I mean, it's a coincidence, sure, but a really small one. A completely fair coin could easily do that. But if you flip that coin 1,000 times and get 1,000 heads, yeah, your alarm bells are going to be ringing. That is a massive, huge coincidence. But here is the real catch. Both of those scenarios are technically possible, even if you're using a perfectly fair coin.
And that actually leads us to this fascinating philosophical musing from our source. It is actually impossible to ever say with absolute certainty that the coin is biased. Just let that sink in. I mean, even if you flip that coin 1,000,000 times and get heads every single time, there is still a microscopic theoretical chance that you're just holding a perfectly fair coin and witnessing the most extreme coincidence in the history of the universe. Because of that tiny sliver of possibility, absolute certainty is it's off the table. All we can really do is measure the degree of the coincidence.
Section 2. The coin flip experiment. Let's apply this statistical reasoning. So, knowing that absolute certainty is impossible, how do scientists and researchers actually make decisions? Well, we're going to walk through a quick hypothetical experiment using a framework that lets us confidently make a judgment call without needing to chase that impossible 100% certainty. Here's our micro-experiment broken down into 3 logical steps. Step 1. We start by assuming the coin is fair. It's innocent until proven guilty, essentially. Step 2. We actually run our experiment by flipping the coin exactly 5 times. Now, let's just say our hypothetical result is that we get exactly 5 heads and 0 tails. Finally, step 3. We calculate the exact chance of seeing a result this extreme purely by coincidence, assuming the coin really was fair to begin with.
Section 3. Calculating the odds. Let's actually put a number on it.
Now, I know I promised we wouldn't get bogged down in math, and I definitely intend to keep that promise. We are merely putting a hard number on the coincidence of getting those 5 heads. Here's the step-by-step breakdown straight from our source. Since a fair coin has a 50% chance of landing on heads, we take 0.5 and bring it to the 5th power, which represents our 5 flips. Then, we do something really important. We multiply that result by 2. Why? Well, because getting 5 tails in a row would be an equally extreme coincidence, and we have to account for both extremes when we're trying to measure how weird our result truly is.
Now, what's really interesting here is the final number we arrive at, 6.25%. If you take a perfectly fair coin, there's exactly a 6.25% chance that you'll flip it 5 times and get a result as extreme as 5 heads or 5 tails. We've basically successfully taken a vague concept, a coincidence, and put a precise objective number on it. If we assume the coin is fair, a result this extreme is going to happen by pure chance about 6 times out of 100.
All right, Section 4, the jargon translated. Let's define some terms.
Now that the underlying math makes intuitive, logical sense to you, we can finally tackle the intimidating scientific jargon that you'll always find in textbooks. You already understand the concepts perfectly, so let's just give them their proper names. First up is the null hypothesis. This is simply the baseline assumption that absolutely nothing unusual is going on. In our microexperiment, the null hypothesis was our step 1, the assumption that the coin is totally fair and boring. It's just the default state of the world before we introduce any kind of new theories.
Next up is the alternative hypothesis. This is exactly what it sounds like. It's the other hypothesis besides the null. It's the scenario we're actually testing for. So in our thought experiment, the alternative hypothesis was the suspicion that the coin was a biased, weighted trick coin. It's the, hey, something unusual is happening here theory.
And finally, the term you are going to hear constantly in science, the p-value. By definition, this is the probability of seeing a result at least as extreme as the one we got by coincidence, assuming the null hypothesis is true. So the crucial point is, that 6.25% calculation we literally just did a moment ago, that was the p-value all along. You just calculated a p-value without even realizing it. It's literally just the coincidence measurement.
Section 5, Bioinformatics in the Real World. Let's apply this.
Now that we've totally mastered the foundation, let's zoom out to the complex real world of bioinformatics. Specifically, we're going to look at a project from our source material involving a lung disease called IPF, just to see how this builds into real-world scientific discovery. I mean, look at this massive contrast in scale. We're moving from flipping a single coin 5 times to analyzing tissue samples measuring the expression of around 18,000 complex genes. But hey, don't let the scale intimidate you. The beautiful thing about statistics is that the exact same logical framework we use to analyze the coin scales up perfectly to analyze thousands of biological data points simultaneously.
Let's look at some hypothetical data for one specific gene, gene 4, and this brilliantly illustrates the real-world challenge scientists actually face. When you look at the data, gene 4's expression appears to be significantly lower in the IPF diseased lung tissue compared to the healthy control tissue. But check out that third column. Random variation is present in both. Just like a coin might naturally flip a few extra heads by chance, biology is messy, you know? Gene expression fluctuates naturally across all samples.
So the ultimate question for researchers is this. Is the lower expression we're seeing in gene 4 just a random biological coincidence, like just a bit of natural variation? Or are we looking at a real underlying pattern of the disease? Basically, is it a fair coin flipping a few extra heads, or is it a trick coin? This is exactly where our friend the p-value returns to save the day in real scientific analysis.
Researchers run a statistical test to calculate a p-value for gene 4. They're essentially putting a number on the coincidence. The rule here is super simple. The smaller the p-value, the more extreme of a coincidence it would be if the null hypothesis, again, the assumption that there's no real difference, were true. If the p-value comes back incredibly tiny, like say 0.001%, the researchers can confidently say, look, this is way too huge of a coincidence to just be random noise. This gene is actually behaving differently in the diseased tissue.
At the end of the day, statistics is never about proving things with 100% absolute certainty. It's about being highly confident that you aren't just being fooled by random chance. Which leaves us with this final, kind of mind-expanding question to ponder. If statistics can never give us absolute certainty, only probabilities of coincidences, what other certain facts in science are actually just incredibly tiny p-values? It completely changes how you view the world of research, doesn't it? Thank you so much for joining me for this explainer, and I really hope you never look at a coin flip or a scientific study the exact same way again.